All right, so those are the equations we're gonna be using. If it's a work in, there's two ways. We can go applied force times displacement, or we can solve for it in the work in, work done by friction, change in mechanical energy. Work done by friction, always gonna be minus force friction times displacement, or in this equation, and this equation fully expanded out is like that. Now, probably I'm gonna start going and say, hey, it goes from here, and I'm just gonna jump to here, and I'm gonna fill in the long equation. On the way in, you should have picked up the sheet that says in class, lack of conservation worksheet. There's 4 different problems. We're gonna go through some of them, not all of them. These are all 2 location problems. So we will be using the work in plus work done by friction is equal to my change in mechanical energy equation. We're gonna be using this one at some point. Okay, but before we use this equation, we have to kind of figure this out, we have to figure this out, and we want to know, is there a velocity, is there a height, is there a spring at location 2? Is there a velocity, is there a height, is there a spring at location 1? So that's kind of what we're going to be thinking about. So pictures are good. We take a look at that first problem. It says there's a 7 kilogram object. A 7 kilogram crate is accelerated horizontally from rest. That means my V1 is 0, by a force of 40 newtons for a distance of 2.5 meters. What is the final velocity? What is my final velocity? What's my V2? Given an applied force of 40 newtons, it says that the applied force causes the object to accelerate 2.5 meters, and hopefully that's implied well enough that the applied force and the displacement, or that you can determine that they're in the same direction. Okay. What's my final velocity? Now there are some other forces here. There is a gravity. There is a normal force. Is there a friction? It doesn't say so, right? It doesn't talk about coefficient of friction. It doesn't talk about it being a frictional surface. So based on that, I'm going to assume, because it's not mentioned, that there is no friction. So it's a location 1 versus location 2. It's going to be this calculation. We're going to use this equation. We're going to use the long equation. So things we're going to want to know, we're going to want to know V1s, V2s. We're going to want to know H1s, H2s. We're going to want to know spring stuff at location 1s and 2s. And we're going to want to know about these 2 works. So let's take care of the H's right off the bat. What's H1? And what's H2? So that makes a lot of sense because it says it's a horizontal surface. To define those heights to be 0, technically you could say that H1 is 10 and H2 is 10. You could. Then you're going to have a PEG at both locations, but they're going to be the exact same mass at the exact same gravitational acceleration with the exact same height. So we're going to take that number and then we're going to subtract from that number. It has no impact. Zeros make a lot of sense to define that height to be 0, but it wouldn't have to be. Okay, so just kind of thinking about that. In this equation, there's questions we're going to want to be asking: is there work in, and is there work done by friction? Is there an applied force?
Yes.
And a displacement? Is there a friction, force friction, and a displacement?
No.
Okay, no, right? So we're kind of trying to, we're going to want to look at those specifically. And the equation for work in is that. So our work in is equal to plus or minus. Which one is it? Is it the plus or is it the minus?
Plus.
Because?
Both of the displacement and the applied force are in the same direction.
Absolutely, because they're in the same direction, it's the plus, which means we're adding energy to the system. So it's going to be the plus of 40 times 2.5, which, if I'm doing my math why am I doing that? Because I'm gonna need it for this equation. I know I'm gonna need to use this equation, and in order to use this equation, I'm gonna need to know these two values. Now, we can, very specifically, if we want, or we could deal with it later, what's the work done by friction?
Nothing.
0, right?
Mhm.
Because there is no force of friction. My force of friction is implied to be 0. So therefore, there shouldn't be any work done by friction. Now, I'm gonna use this equation. The equation that's listed on your formula sheet is written like this. Okay, it's written like this. Change in mechanical energy is ME2 minus ME1. ME2 is these three energies at location 2 added together, minus ME1 is those three energies added together at location 1. Are you okay with me? Do you want me to start here and then go to here and then go to here? Or are you okay with me just going, I know this is what's listed on your formula sheet, are you okay with me just writing this out directly?
Let's do those.
Okay, which means you either need to know how to derive this from this, or you just remember that this is the fully expanded form of this. I'm gonna erase this in a second just because it's gonna be my way. But our full equation is that. Okay, work in plus work done by friction. This is ME2, this is ME1. Before we start plugging in numbers, I want to simplify this and cross some stuff off. Work it. Yes or no? Is there work it? Is there an applied force and a displacement?
Yeah.
Yeah, right, and we've already determined, we already calculated that. That's why I did that step, because it needs to be there. The work done by friction, yes or no?
No.
No, because we said it's no friction, work done by friction is also gonna be 0. Now we're in the same questions we asked ourselves back before semester. Is it moving? Is there a height? Is there a spring? So at location 2, is there kinetic energy?
Yeah.
Because is it moving at location 2?
Yep.
Yeah, we don't know how fast, but that's what we're solving for, and that's where it's gonna come in. Is there a height at location 2?
No.
Is there a spring at location 2?
No.
Is it moving at location 1?
No.
It says it is accelerated from rest, that's why we said that was 0. Is there a height at location 1?
No.
Spring at location 1?
No.
So this simplifies down quite a bit. Before I plug in numbers, I'm gonna do one last kind of expansion. KE2 is 1/2 mv2 squared. My work in is equal to 1/2 the mass of my object, 7, times, oops, sorry, we have a number here, that should be a number. My work in is positive 100, which is equal to 1/2 the mass of 7 times V2 squared. Sure?
Hey, how's it going?
Good, how are you?
Good.
What are you doing in here?
They are right to your right, right under there somewhere.
This guy.
Thought I got rid of you.
Well, I wish.
So sorry you gotta deal with that one. Good night.
So 1/2 of 7 is 3.5. $100 divided by 3.5. So we divide both sides. 28.57. And there's there's more digits on my calculator, but that's all I'm gonna write. However, I'm gonna use the full, I'm gonna divide by my answer. And then because we have to take this, I'm sorry, not divide, we got square root. So we take the square root of, because it's V2 squared, V2 is equal to 5.345, so 35 meters per. V2 is 5.35 meters. It's a two-location problem, so we're gonna have to use that big, long equation. We're looking for velocities at two locations, heights at two locations, springs at two locations. We're looking for work in because there's an applied force and a displacement. We're looking for work done by friction, force friction and displacement. So we're plugging in numbers. Clarifications on that? All right, then let's look at the second one. The second one is almost identical from the standpoint of there's an applied force of 40 newtons with a displacement of 2.5 meters to the right on a 7 kilogram object that starts from rest. And we're trying to determine how fast they're going. The difference is what? I'm sorry, I'll give you a chance to read through that. Read through the second one quick. What's the difference between the first one and the second one?
Just some friction.
There's friction this time, right? So this time, there's a coefficient of friction of 0. What is it, 2?
We got 0.2.
0.2. Now, last time, we said there was a force of gravity, we said there was a normal force, but we didn't calculate, because we didn't care about those two things. Officially, I don't care about those. No, let me rephrase it. Directly, I don't care about those two forces. However, I do care about those forces because now there is a force of friction. And in order to determine or to calculate that force of friction, I need to know that normal force. So I'm going to pause for a moment, and I'm going to ask you to determine what the force of friction is. Based upon a mass of 7, an applied force of 40, coefficient of friction of 0.2. Green formula sheet has your force of friction equation on it. Probably want to pull that out. Oh, I can tell it to you too. Just for the record, force of friction is equal to mu times the normal force, and our force of gravity is equal to m times g. So those are the two equations you're probably going to need. If you calculate the force of friction, All right, so in order to calculate the force friction, you're gonna use this equation. But you need to know the normal force. And what's the normal force value?
The same as that.
And how do we calculate that? We take 7 times 9.8, so 68.6?
Yeah.
Okay, so 7 times 9.8 is your F of G. Because your forces are balanced or unbalanced in the y direction,
Balance.
they're balanced, then that means this is also gonna be 68.6. So then what's 68.6 times 0.2? Your F of F is gonna be 13.72 newtons. Gonna be 13.72 newtons. Okay, so then this is 13.72. Why is that important? Because in order to use this equation, we need to know work in and we need to know the work done by friction. And this time, is there work done by friction? Yes, because there's a force. And that's why that's an important step. So I'm gonna erase all this stuff. So in that long equation, we're gonna have to know work in and we're gonna have to know work done by friction. We're gonna have to calculate those two things. So I know it's the exact same numbers as the previous one, but for sake of practice, how do we determine the work in? Well, we use the work in equation, which is gonna be plus or minus our applied force times our displacement. Our work in is gonna be, is it the plus or is it the minus?
Plus.
Because,
They're the same direction, though.
Correct. so because my applied force is to the right and my displacement is to the right, same direction, they're gonna have a positive 100 joules worth of energy are gonna be added to our system because of the applied force and displacement. That's my work in. The work done by friction is minus our force of friction times our displacement. Our work done by friction is equal to the opposite of our force of friction, 13.72 times 2.5, which is gonna be negative. Friction always opposes motion, therefore the work done by friction is always going to be negative. Is gonna be a negative 34.3 joules, which means energy friction is going to remove negative 34.3 joules worth of energy. Now, two location problem. Work in plus work done by friction is equal to change in mechanical energy. If we expand that thing out, my ME2 is KE2 plus PEG2 plus PEE2 minus KE1 PEG1 PEE1. That's my fully expanded equation. Anybody want me to talk about that, or are we okay with me just writing that? Okay, now let's look at our stuff. Is there work in? Yeah, right, it's gonna be 100, keep it. Is there work done by friction?
Yeah.
Yeah, keep it. Is there kinetic energy at location 2?
Yes.
Yeah, it's moving at location 2, we just don't know what it is. Is there a height at location 2? And oops, I forgot to say. What's my H2?
0.
And if H2 is 0, what's my H1?
Also.
Also gonna be 0, right? So is there a PEG2?
No.
Is there a PEE2?
No.
Why not? Because
There's no springs.
no spring at location 2. Is there a KE1?
No.
Why not?
Because it says it's starting from rest.
Right, there is no velocity at location one, it starts at rest. Is there a PEG one?
No.
No height at location one. Is there a PEE one?
No.
No, because there's no spring at location one.
I'm glad you.
Work in, work done by friction, is equal to KE2, which I'm gonna expand out before I plug in numbers, is that. So it's pretty similar to last time, except for now this exists. Plug in my work in that we already calculated, positive 100. I'm gonna add a negative. So are you guys okay with me just saying add a negative? I can just say minus 34.3?
Yeah.
Or would you rather have me go plus parentheses minus 34?
No, minus is
We okay with that?
good. Yeah.
Okay. Is equal to 1/2 our mass, V2 squared. 100 minus 34.7, I think, is 65.7.
Yep,
Yes.
yes.
Which is equal to 3.5 V2 squared, because 1/2 of 7 is 3.5. 65, clear, 65.7 divided by 3.5. And divide both sides by 3.5 is 18.77. Is that V2?
No.
No, that's V2 squared. Take the square root of, no, it's not really 0.77. It's a lot more digits, so I'm not gonna take the square root of 18.77. I'm gonna take the square root of my previous answer on my calculator, full decimals. And my V2 is 4.33 meters per second. Is that number bigger or smaller than the previous calculation? Smaller, why?
It's just friction.
Because friction removed energy from the system. What kind of energy did it remove? Kinetic energy. It's going slower because it removed kinetic energy from the system. Questions on that? We're not gonna do both of those two. We'll talk about the third one, but we're gonna do the fourth one. So the third and fourth are very similar. We have a baby who's in their baby sled. They're at the top of a hill, and they are moving slowly at 2 meters per second on a 15-meter tall hill. If you push them at 10 newtons for a distance of 2 meters, so you're gonna push them all the way down the hill, you're just gonna push them for like, this is about 2 meters, so a little over 6 feet, 6.5 feet. You're gonna push them for about 2 meters. How fast will they be moving once they get to the bottom? And I don't know why it says hint, because it's not really a hint, but don't worry, they're wearing a helmet, because if it's a frictionless surface, guess what's gonna be true about the speed? It's gonna be pretty high, right? It's almost an ME1 equals ME2 problem, except for there is an applied force because there's a work in. Right? That's if it was a frictionless surface. Now, that's not really the case in most sledding hills that you've ever gone to. Most of the time there is friction, unless you go to George Street shortly after, or like in the spring, where you get that, well, there's still gonna be friction, but that, you get that like early, during the day, slight melt, and then it freezes at night, and you just get like ice on George Street Hill, and then it's like impossible to walk up the hill. Then your coefficient of friction is gonna be pretty small, and there's gonna be a low friction, but there's still gonna be some friction. Or, friction on this hill would be if you took like your saucer, and you took that experimental non-stick spray that they put on cereal so they don't clump together in the box. National Lampoon's Christmas Vacation reference, where and then you go sledding. Okay. Anyways, there's gonna be friction. So that's what the third one is. Or the third one's frictionless. The fourth one is almost the exact same problem. This is the one we're gonna do. There is some friction. Now, because of the kind of the nature of the hill, you could almost consider this an inclined plane or a right triangle, right? If it wasn't so curved, we could draw that. The problem with a hill problem is if there is a hill, then what we have, oops, that's supposed to be my babies.
Yeah.
That's a big kid. Couldn't say.
Kind of look like a penguin with their beak.
It's like half the size of the hill.
That's an awful baby. It's okay.
That is most definitely not a.
That is totally, that's a beautiful baby right there. All right, so they are on the top of this hill that is, and they have a mass of 10 kilograms. So they're about 22 pounds. They're pretty young babies. They aren't going quite fast enough, so we're gonna give them a little push. Now, the tricky thing about friction on a hill like this is when we calculate, if we were to calculate the force of friction, I'm gonna erase this in a second, so don't write this down, is mu times my normal force. We've always been in this really idealistic world where my normal force is always straight up. That's because it's always perpendicular to the surface. However, in this, if this was my baby, this is my normal force, and this is my gravitational force. It's not this simple XY coordinate system like we've been used to. Then we would have to do trig functions. Well, Mr. Davies, you said we don't do trig functions in conceptual physics. You're right, we don't do it. That's why I won't give you a coefficient of friction on a problem like this. I could give you a force of friction over some distance, like how far down the hill do they go, like the hypotenuse, then we could determine it that way. I don't do it that way either. In this particular problem, the fourth one, I specifically say the energy lost due to friction is negative 1,467.3 joules. Is there friction?
Yeah.
Yes. What's that doing? It's removing energy from the system. The work lost or the work done by friction is negative. Lost, work done by friction is always going to be negative, is 1,467.3. Okay, now, it's a two location, question mark, how fast are they going at the bottom of the hill? At the top of the hill, they were going 2 meters per second. They were going 2 meters per second. They were going 2 meters per second, but they weren't going quite fast enough. So you being the good aunt or uncle that you are, decide to give them a push for 2 meters with an applied force of 10 newtons. Now, why do you only push them 2 meters? Because you tripped and you fell on your face. Because you didn't want them to go too fast. Because, I don't know, you stopped after 2 meters. You got tired of it. Too much work. I don't know why. Okay, now, this is gonna be a 2-location problem. We're gonna use that long equation. We're looking for V1s and V2s, we're looking for H1s, and we're looking for H2s. What's my H1?
15.
And if my H1 is 15 meters, then what's my H2? Okay. Could you define that differently? Sure, you could. I don't think I've seen anyone define it different than that. But you could. Is there any springs here?
No.
Any springs here?
No.
Don't care about spring stuff then. We will be using the long equation, which means we need to know work in and the work done by friction, already given. What's our work in equation?
Applied force, well, plus or minus the applied force times the change of energy.
Correct. Do I expect you to memorize those equations?
Well, not.
No, I don't. Okay, it's on the formula sheet. Okay, so work in, is it the plus or is it the minus?
Plus,
Why?
because you're going in the same, what is it? The applied force and the way that they're going
Mm-hmm.
in the same direction?
Yep. So you're pushing the kid down the hill, the applied force is down the hill, they're going down the hill, same direction, same positive. You're adding energy to the system. You're gonna make them, hopefully, in theory, go faster. 10 times the displacement that you pushed them. Not how far down the hill did they go, how far was that applied force applied? And it's 2. So the work in is gonna be 20 joules. You're adding 20 joules of energy to the system. You're gonna add 20 joules worth of energy to the system. Now, long equation, work in plus work done by friction is equal to, I'm gonna expand it fully out right away if you don't mind. Sure don't, Mr. Davies, you go right ahead. Thanks. Don't mind if I do.
You doing it right now?
Yeah. He's definitely wasted. This is so long to remember.
There's the long one. Give me a second to write that down.
Marker on the hand.
Yeah, I shouldn't probably use my fingers as an eraser. If only I had erasers. That would-
Yeah, you have like what, 4?
Yeah.
Solid.
Well, actually, 5, because this one's got a built-in eraser.
There it is.
So chill.
Stand by.
Yeah.
Gotcha. Okay, so work in plus work done by friction equals that ME2, KE2, PEG2, PE2 minus ME2, ME1, KE1, PEG1, PE1. So we ask ourselves a bunch of questions. Is there work in?
Yes.
Yeah, right? It's gonna be 20, we'll add that in a little bit. Is there work done by friction?
Yes.
Yeah, it was given in this problem. There was friction, therefore there's gonna be work done by friction. Now we're comparing 2 locations. At location 2, is there kinetic energy?
Yep.
Yeah, because there's gonna be a velocity, we are assuming there's gonna be a velocity because that's what we're solving for. At location 2, is there PEG?
No.
Because we define that height to be 0. At location 2, is there a PEE?
No.
Because we said there was no spring. At location 1, is there KE1?
Yes.
Because it's moving at location 1, right?
Mhm.
The baby was moving before you pushed it. So there is a KE. At PEG, I'm sorry, at location 1, is there a PEG1?
Yeah.
Yeah, there's a height at location 1. Is there a PEE?
No.
No.
Because we said there was no spring. I'm not gonna plug in numbers quite yet. Work in plus the work done by friction is equal to parentheses. I'm gonna color code this just to try to help show the difference, at least initially. That's my KE2. That's all of my ME2. Is everything else canceled out? Minus minus KE1, which is 1/2 MV1 squared plus PG1 is that. Now remember, order of operations, parentheses, exponents, multiplication, division, addition, subtraction, something like that, I don't really remember. But you gotta do the parentheses before you do that subtraction, just keep that in mind. So you gotta do your multiplication of these, and the multiplication of these before you add these, but you gotta do these parentheses before you do that subtraction, so just keep that.
Plug in numbers time.
All right, so my work in, we already calculated, would be a positive 20. That's my work in. I'm adding 20 joules worth of energy. The work done by friction was given as it was losing 1,467.3, which is equal to 1/2 of the mass of the baby times V2, so that's 10, V2 squared, parentheses, minus, parentheses, 1/2 times 10 times 2 squared plus
10.
10 times 9.8 times. See, by me changing my voice like that, it's like, whoa, I'm focused now. It's not just him writing numbers on the board, it's interesting him writing numbers on the board, and change your voice, call it information, and then you're like, what?
This is
No,
like
Action now.
this is like stand-up comedy right here.
See, now I'm-
Good thing I'm recording it.
I'm
This
sorry
is
to
gonna
see
go
you.
viral, I bet. I hope not for a bad reason though. Normally, I feel like it probably was though, that's a bad reason. Negative 1447.3, right? 20 minus 1,004.
Yeah, good, wow.
Negative.
If you did that
Is
right.
equal to 5, 1/2 of 10,
Yep.
v2 squared, minus parentheses, 1/2 of 10 is 5, 2 squared is 4, so 4 times 5 is 20, plus, I don't know that number, 150, whatever 150 times 9.8 is. 1,407. Right? 10 times 9.8 times 115 is 1,407. Order of operations says I gotta do this parenthesis thing first, so that's minus 1447.3 is equal to v2 squared minus, that's gonna be 1,490. Now I'm gonna underline something and ask something and maybe make an incorrect statement. Do I subtract those two things right there?
No.
Why not?
Because, the one has the thing in it. Variable.
Yeah,
boy.
the thing right there, it has that thing, right? So
Yeah.
are those like terms?
No.
No, so we cannot add those, we cannot subtract those two numbers, they are not like terms. There's this thing called an unknown variable, this thing does not have the unknown variable, so therefore can't combine like terms. So algebraically, how do I get this to the other side?
Add.
Because that's a minus, so don't divide it, I have to add 1,490 to both sides, which is gonna give me 43.8. Please look, there's a calculator.
All can be, there's a calculator right there.
Yeah,
did, yeah.
because my head was not working very well as one. Is a positive 42.7. 42.7, yes. And that's equal to 5v2 squared. Divide by 5, divide by 5. 8.54 is equal to v2 squared. Is that my final answer?
No.
No, because that's v2 squared, so we need to take the square root of those numbers, of that number, I should say. My v2 is equal to 2.92 meters per second. Now, for some reason, that number doesn't seem quite the same number that I got last hour, but
I think it seems
I think I did it. I hope I didn't screw it up.
No, that's, you're good.
That much amount of work, it can't be wrong.
Well, no, it's most definitely right.
Okay, so based upon what I did, I think this is, I'm pretty confident in this. It just seems like the decimal's off, but I just probably don't remember the decimals correctly. Okay, so what would happen if there wasn't friction? Well, this removed a fair amount of energy, right? If basically the amount of energy that friction removed is almost equivalent to the height of the hill, so therefore, that baby would be moving really, really fast, right? That's why in the previous one, they had a helmet on. So that's what we can do with a two-location problem when there is friction, and this is kind of the workaround in terms of like, well, what if there was this incline plane? Your homework for tomorrow, I kind of changed it last minute from in the last hour. It's not what I had planned. It's this thing that's called Progress Quiz 6.2. It's not linked in Canvas yet. I will do it in like the next couple of minutes. Just to be clear, this thing says Progress Quiz 6.2. Last semester, you also had a progress quiz that was called 6.2. Do this Progress Quiz 6.2, not that one. This one has work in it The other one was just ME1s, ME2s, okay? So I modified the 6.2 last semester to meet the needs that we had last semester, but this is one that I had already. I should have retitled it before I printed it, oopsie-doo. Okay, couple things here, I forgot to give or I didn't give you the answers because this was a progress quiz and not a homework assignment. However, it's a homework assignment now. So the answers to your progress quiz, which is your homework, are right here. And I quickly worked them out at the end of last class, and I hope I worked them out correctly, but those were the answers that I got, and you should probably write the answers on your little sheet. And if for some reason I screwed something up, please notify me right away, and then I can make a correction to this, but there's 3 parts to number 1, A, B, and C, and then this is question number 2 has an answer of 5.67 meters per second. Yeah, there are 2 location problems eventually, most of them are. So that's your homework for tomorrow. I'll get that built in Canvas here shortly, and I'll get it posted. So if you have any questions, let me know. If you have questions about your lab, that stair lab, before you leave, maybe you want to ask me that, because that's a lab grade, not a practice to learn grade, and it has a bigger impact on your overall grade.